Bismillahirrahmanirrahim. Again, before starting today's session, if you have any question from the last session, we can discuss first. It seems that you don't have any question at this moment. Okay, so please go through the lectures. Okay, so if needed for several times, because this understanding is very, very important. Okay, in the last class, we have discussed about this example where this is a combined approach which contains both time domain sequence, a continuous signal to the discrete signal xn, from the xn how to find from xn how to find xk, and from the xk how you can come back to xn. Whenever we are defining xn, we need two things. One is what is the magnitude of it. So xn, this is the magnitude of that. So it should be mentioned as the amplitude of this one, as well as what is the frequency, actual frequency of this signal. These are the two information we need from this xn. And we have also shown that how to draw the xk with specific notation. For example, this one, where we have found this is our result at a location of x1, and definitely we found that this is the mirror. That means you should have the symmetry both in the left side and the right side. So we are expecting the repetition, and that's for sure. However, whenever we will go for the inverse discrete Fourier transform, what we are doing, we are adding this point, this point, this point, this point, and make it an average of that. And that is our inverse discrete Fourier transform according to this formula. So you can go through this example, and it will definitely help you to understand the full process. Okay. And please also do these two examples whenever you will return the script for fs equals to 8 Hz and n equals to 8, and fs equals to 4 Hz and n is equals to 8. So you will find some definitely interesting outcome over there. Okay. Okay, before going to the next step, what is our perception of the upcoming section? For example, I have already mentioned that whenever we are, let's say, we are talking about, okay, we are talking about this x omega. We have mentioned that this is a continuous one. So let's say there is an example where we have found our x omega, the magnitude response, like as follows. Let's say this is like this. This is from 0 to pi, and of course it will make the same kind of figure in the opposite way, from pi to plus pi. Okay, so I tried my best to make it similar to the left to the right one, so twice pi. Okay, so what is our range of view? Of course, from 0 to twice pi. Obviously, if we have the information from 0 to pi, that is also enough for the calculation, because you can do the repetition in that case. Okay. Now, this axis is omega, which is a continuous value of the omega. It preserves the continuous value of the omega. Now, if we want to find the value of x k, That means our target is to show the xk with certain sample numbers. Okay, so as we have mentioned that whenever you will try to find the xk, it should contain certain number of samples. For example, here, let's say we are giving how many samples? Let's say 10 samples. So 0 to n minus 1. So 0 to, let's say, 11 minus, 10 minus 1. So that is 0 to 9 is the sample. Okay. So how we can sectorize those things? Let's say try to make it like this. This is 0. So let's say 1, 2, 3, 4. Let's say this is the 5, 6, 7, 8, 9, and 10. This 10 basically belongs to the next cycle. Okay. So here, let's say this is the case. So in this scale, this black one, this is the scale of k. So how the xk looks like? It certainly looks like this. At 0th sample, we have the stem. At this one, we have the stem. At this one, try to understand, we have the stem here. We have the stem. We have stem there, and so on. Okay, we are now just considering, try to concentrate between 0 to pi and try to find that. So whenever we can write this, we are finding the value of xk. What is the problem? The problem is you are missing some values. Of course, you are missing some values. For example, here, which frequency component actually have the higher strength? You can find that, of course, in this case, let's say I am writing this. In this case, this point represent the maximum strength between 0 to pi. However, unfortunately, you are missing that point because you are only dealing with this point, then this point, this point, and this point, and this point. And this is obvious whenever you are making the discretization of a continuous domain to a discrete domain. Of course, there is a chance to missing something from the actual value. So that definitely makes some impact in your domain of the xk. So that makes some issue, of course. Another example can be given very practical, showing the practical scenario. Let's say in the x omega, how we got this x omega? Let's say we got it from xn, where xn is equals to, let's say, cos twice pi divided by n into r into n. So we have done this kind of example, where this r, let's say this r is equals to some value. So how we got it in the earlier section, we have mentioned it. That means at the location of r, you will get a stem, and another stem will be performed at the location of n minus r. Let's say this is the section of that n minus r, where this is, let's say this is your twice pi, and this is the 0. Where is the pi? This is the pi, and this is the middle. Okay, so this is, you have the repetition in the both side. Okay. Now, whenever you are doing this, you are making this xk, you try to find xk. So this is x omega. Of course, in the x omega, you will find this kind of thing. because you have only a single frequency component in the xn. So if you do the Fourier transform, that is discrete time Fourier transform, you will find these two stem. There is no question about this. Now, if you want to find this xk, let's say, where are the points for the xk? It depends on the value of n, capital N. It depends on the value of capital N. In that case, let's say you are planting those points like this. Okay, just approximately the points are like this. What happens? In this case, you will definitely missing this point. You are not getting this one, and you are not also getting this one similarly. So that makes a problem. And in that case, what will be happen? What would be the output? Number one, and how you can solve this problem. What would be the output, predicted output, and how you can solve this problem? I believe that you understand the problem. Whenever you are sampling your continuous domain, of course there is a chance to miss your signals, your targeting signals. Okay, let me show this problem and the solution with that example. Okay, so we know that already from our past experience that what is the jump, and jump is twice pi divided by n. So that means you can say the jump from the frequency perspective. From the frequency perspective, the jump is like twice pi into 1 by n, where twice pi represent what we have known that it is already known that the twice pi represent fs, actual frequency, into 1 by n. So we can say that what is the jump? The jump is from the actual frequency, that is fs by n. That is our jump from the one frequency to the another frequency. So always we start with the 0. The next frequency we can target, that is fs by n. Target means that is our known frequency according to the Fourier transform. What we want to do, xn is the unknown frequency. We want to match it with our known frequency fs by n. If it match, then what happens? For the 0, okay, let's say we are not getting any match, so 0. For fs by n, if you are getting any match, okay, fine, you will get a stem. Otherwise, you get 0 value if it will not match with our xn. Then the next one is what? fs by n into 2. You want to match with this xn, and this is the 0, this is 1, this is into 1, and this is a 2. So if doesn't match with that, you'll get 0. Let's say you are continuing the process fs by n into 3. Ultimately, this one actual frequency, you try to match with your xn, and okay, you are getting some result like that. Okay, so you are getting some stem like this. So in this process, you are going forward. However, in the xn, if you have some other frequency in between 0 to fs by n, or fs by n to twice fs by n, you are missing these points. You do not have any clue whether is there any frequency component over there or not. So that is the shortcoming of this kind of processing. Okay, let's start with one practical example. Example here is given as xn is equals to half for n is equals to 0 and 1. And for other samples from 2 to 9, those are zeros. Practically, what happens? 2 to 9, yeah. So this is from 2 to 9. There should be 9 here. Okay, so actually, how we are representing this signal? This is half, and this is half. That's it. Why we are putting these zeros? Okay, we are putting these zeros to extend the value of k as well. If we do not put these points, what is the range of n? The range of n is from the range of n is equals to 2. That means only 2 samples. So the k is also from 0 to 1. 0 to 1. So only you can find 2 samples. Now what we are doing, we are padding with zeros so that we can extend the number of capital N from 2 to 10. We are increasing the value of n here. Why we are doing this? Okay, so the step number 1, we need to find the xk. So xn e to the power minus j twice pi k by n into n. So conventionally we are writing is like this, minus j twice pi divided by n into k into n, or you can write e to the power j twice pi k by n into n. Okay, because this part remains constant and this is a variable, the k is the variable. Okay, fine. So now putting the value of n for different value of n, we know that the n is from 0 to 9. We can get these values. For n is equals to 2 to 9, all the values are zeros, because at that moment the magnitude is 0. That means x2, x3, all the values, they are representing 0. That's why they will resulting the value as well as 0. So we have only these 2 components, and from there, by doing the mathematical process, mostly the Euler's using the Euler's identity, what we have found this equation. Okay, so very simple, where we have found the cos pi k by 10. So that represent the frequency of that sequence, and here we have the phase as well. Okay, whatever the things, whenever we are writing the magnitude response, of course we want to consider only the magnitude part, do not consider the phase part. Okay, of course it should be looks like a cos signal, and put the value of k there. So for k is equals to 0, you will find, of course, this is 0, cos 0 is equals to 1. For k is equals to 1, for k is equals to 2, k is equals to 3, 4, 5. And of course, that is the mirror, and you will get the exactly the same things on the other half. Now the question is, can you draw this magnitude response if we took the n is equals to 2? If we took n is equals to 2, how it looks like? You have only 2 samples. You have only 2 samples. What are the samples? Let's say this one and this one. Those are the 2 samples you will get. You will get basically these 2 samples. And because what is the range of view? Your range of view is from 0 to twice pi. So within 0 to twice pi, how many samples you should have? Only 2 samples. So you are missing this whole spectrum. That means this scenario. So by knowing these 2 samples only, this sample and this sample, what you can say? You can only say that, okay, yes, we have the DC part in our signal. What was our signal? The signal was like this, half and half at n equals to 0 and n equals to 1. That is a typically low pass filter. You already know that. So this is a low pass filter. If we only take these 2 samples, we do not pad it with zeros, what happens? You are getting only these 2 stems, and it will basically confuse the researcher whether this is a low pass or high pass or band pass. You never know. So that's why this is very important to extend this signal xn with some zeros, padding zeros. If you improve this with n is equals to 20, what happens? We have taken it for n is equals to 10. Of course, that improve the scenario, and you can now obviously tell that, okay, yes, it is a low pass filter. Now, if someone choose n is equals to 20, what happens? You are getting another samples in between, which actually shows that yes, you are more confident about your signals. Okay, so in some cases it might happen that you have this, you have this, you have this. It looks like a low pass filter, but it might happen that, so how many points you are taking? You are taking 0, 1, 2, 3, and 3. So let's say 6, 3 and 3. Let's say 7 samples. Now, if you improve or increase the samples, it might happen that it is not following this process. Okay, if you increase the samples, it might happen that you are getting something like this, and then like this, and like this. It might happen. So then you are, that looks very interesting. You can find that, okay, this is not a low pass filter. It looks like a band pass filter. Maybe it's a band pass filter. Now you can improve more samples. Okay, let me improve more samples so that we can understand more about the filter. And it might happen that you are getting something like this, and you have found that, okay, it is more interesting, and you got the response like this. Now the response looks like this. The filter response looks like this. So what I'm mentioning you, to understand the filter or the system properly, what you need to do, you need to go for at least a handsome amount of n, so that you can understand the profile of the filter. Very low number of n will misguide you completely. So there is a possibility. So that is why it is very important, whenever you have only these 2 samples, that should be padded with zeros, so that you can understand the profile properly. Okay. Okay. Now there is another example. In the previous example that has been given in the time domain with these 2 samples, and this is a aperiodic signal. So for the aperiodic signal, you should get the spectrum, a continuous spectrum in case of x omega. From there, whenever we will move to the xk, we'll get some stem like that. Now in the next example, we can take this as an example where this is a continuous, the periodic signal, and you can closely look at this frequency. We have twice pi f twice pi omega is equals to twice pi fn. So this f can be replaced as, this is f is equals to 11 by 40. So that means that represents the frequency. That represents the frequency. Okay. So for this one, just arbitrarily, we can choose n is equals to from 0 to 19. So the capital N is equals to 20. We have choose that. Okay. So similarly, what we can do, we can find the xk and do it yourself. You will find this result. So this cos part can be represented as this by using the Euler identity. Okay, so this is very simple. You can do it, and after doing that, you are multiplying with e to the power minus j twice pi by n into kn. So according to the formula, here the capital N is equals to 20. Okay. Okay. So here for the first term, we have this, And if you want to perform the mathematical part, I have just give you the hints. Okay, so for this kind of process of the mathematical process for the the polynomials, you can derive it from your previous mathematical background. So I have shown it for the first part. You can do it also for the second part as well. So you will find the result like this for the first one. From there, you can also find this is the final result. Okay, so from this you have got this one based on this formula. Okay, so at the end, what we have found here, this is the value for the xk. This is the value for xk. For the xk, we are getting the result like this. Okay, so this is the result. Maybe this is not in a proper scale, but what we are showing here, try to understand at the location of 5. So that means at k is equals to 5 and at k is equals to 6, you are getting a higher match. Maybe these numbers are should be like this. Okay, just draw it like that, and sudden drop is like this. Okay, and that will follow the same thing in the other way. So what we are showing here, for k is equals to 5 and k is equals to 6, we are getting the maximum match compared to the other points. Why that is so? Because as we can understand that the equation was our xn, it was like cos twice pi 11 by 40 into n, where 11 by 40, it is very close to 11 by 40, which is very close to the 5 by 20. Why we are talking about 5 by 20? Because in case of Fourier transform, we have e to the power minus j twice pi k by capital N into n. So we basically, what we are doing, we are matching this the unknown signal with this known signal by changing the value of k. Whenever you are changing the value of k, that certainly changes the frequency. So when k is equals to 0, of course, that is e to the power, what is the frequency, minus j twice pi 0 by capital N into n. That certainly shows the DC value. So whenever we are talking about the DC value, what is the match? We have found that, okay, the DC value is there and this is the value. Whenever we are talking about k is equals to 1, then we have e to the power minus j twice pi 1 divided by n. N is what? N is 20 into n. So what is the frequency? This is the frequency, twice pi 1 by 20. That is the frequency. Twice pi 1 by 20 is the frequency. They try to match with your unknown signal. And definitely we can say that no, this is not very close to this one. So that's why we are getting some result like that. Whenever we are extending this at k is equals to 5, what happens? It will give e to the power minus j twice pi 5 divided by 20 into n. So 5 divided by 20 means 1 by 4, which is very close to 11 by 40. So if you go for the fractional calculation, so if I open the calculator and I try to find what is the value of 11 divided by 40, it gives 0.275, and 1 divided by, this is 1 divided by, let's say 1 divided by 4, that gives 0.25. So they are very close to each other. When they are very close to each other, they are giving the higher match. The frequency definitely higher match, and they gives a very high energy to the output. Whenever we are taking k is equals to 6, what happens? The e to the power minus j twice pi, 6 by 20 into n. 6 by 20, it shows what? 6 divided by 20, it gives 0.3. And as we already found that 11 by 40, it gives 0.275, something like that. So they have also very close match, and that's why we are getting higher value there. Whenever you have k is equals to 7 equals to 7, definitely the matching will be reduced. The frequency matching will be reduced, and that's why you are not getting any value. Theoretically, try to understand that. Theoretically, all these values should be 0, but practically, for the mathematical purposes, there are certainly you are getting some numbers. But if I write the graph properly, you will find this kind of phenomena. Let's say this is at the location of pi, and this is 0, this is 1, this is 2, this is 3, this is 4, this is 5. Maybe should erase this pi. Maybe other numbers are there: 6, 7, 8, 9, and then this is 10. So at the location of 9, maybe this is pi. So at 5th place, you should get the maximum similarity. At the 6th place, you get second maximum. And for the all other places, you might have this kind of scenario. And like that. So from there, what we can understand, the given signal xn is equals to cos twice pi 11 by 40 into n. Is that a single frequency or it is a compound frequency? Of course, this is a single frequency. However, we are getting two matches over there. It shows that whenever you are choosing the value of n, certainly the value of k by n for any value of k, it will not match 100%. It is not matching 100%. How can you match these things? Is it possible? Previously, what we are taking, n is equals to 20. Can you give me one solution how we can catch the specific frequency? 11 by 40. Then what would be the process? How we can solve this problem? We are not getting the exact result here. So how we can solve this problem? One process is a very simple way, that if I take n is equals to 40, then what happens? At the location of k is equals to 11, what is the range of k? If I took n is equals to 40, it should start from 1 up to 39, isn't it? If that is so, when k is equals to 11, we'll find e to the power minus j twice pi 11 by 40, and then it will match exactly, this will match exactly with your unknown signal. And in that case, you will get only a single jump at the location of k is equals to 11. And where should be the another one? Any of you? This is
40
sorry?
40 minus 11.
Yeah, 40 minus 11. Nice. What is the value? 29. So that is 29. So at the location of 29, since this is a periodic function, you know that So this is, you can say that this is your R and this is your N minus R. Okay, so you'll find this is at the location of 11. So you'll find these two stem and all other samples, let's say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All the samples are 0 now because there is no match, and we have complete match over these two samples. Okay, so the solution could be given like this. Here it shows in a different way. Here the signal has been changed. Okay, but if the signal is still like that in the previous section, I have already shown you that how to catch that frequency, So even though if it is 11/40, you can catch it by increasing the value of N. That is the key point. Okay, just to show it practically how it works. If the signal is like this, okay, so let me check the previous section. Maybe is there any mistake in the notation? Okay, yeah, there is 2. I was just wondering whether I have given the 2 there. Okay, so now you can find that if we took N is equals to even 20, then what are the values we are getting? This one, 10/40, it is equals to 1/4, isn't it? So whenever the K is equals to, let's say 5, at that moment we have K by capital N is equals to 5/20, and which is 1/4. So at the location of K is equals to 5, that will give super match. So 100% match. So what we are expecting with the same example you can do, we are expecting that at K is equals to 5, that will give the highest. Okay, can you hear me?
Yes, sir.
Okay.
Yes, sir.
Okay, due to the internet issue, I have lost the connection. Okay. Okay, the recording is still going on, so probably you can see the screen. Okay, so I have already mentioned that in this case, the second case, whenever we are taking a different signal, the signal is representing this. This is cos twice pi 10/40 into N. That is the signal frequency. So whenever we are taking capital N is equals to 20, so for K is equals to 5 at that point, so we have the super match 5 divided by 20, which is 1 divided by 4, which is equal to 10 divided by 40 is equals to 1/4. So they have matched the frequency. Basically 10/40 is 1/4. So we have 1/4 there. And we have got the maximum match at that location. And you will find the same value, a repetition at the location of where N minus 5, and which is nothing but this 15. Okay, so we'll get the mirror in between, and you will have the repetition, same repetition over there. Okay, so I believe you understand the things very easily, why we should take higher number of N, and that always give us some probability to catch all the signals or representing all the signal in a proper way. However, whenever you are improving or increasing the number of N, that will mathematically and computationally take some time and some memory location. So that's why we need to think about the processing, whether we need a high value of N or the small value of N is enough for the processing. Okay. The second topic of today's lecture can be how to find the x omega, that means the continuous one, from the xk. That is very important. Let's say you have the xk, and now you need to proceed. You need to proceed to x omega, the actual one. What is the purpose of this? Let's say you have your continuous time signal. You have discretized that xn at your office with your instrument, and then you have found the value of xk. Now you want to send these values via some transmission medium to some other port, and they are getting xk, exactly xk. However, this is the first area, that means your area. You have the computer at your office and you are done this kind of processing with your computer. But whenever you are sending this document, so based on the bandwidth of the channel, you are minimizing that, and that's why you are making this n limited, or based on this number you are finding the value of xk. You have sent it to the other location. Now they receive xk and they try to understand what was there actually, so they want to make it x omega by using the xk. So that's why this is important, and as you know that x omega will give you detailed understanding of the signal. So as we know that x omega is equals to this is according to the discrete time Fourier transform. Discrete time Fourier transform, and or this is Fourier transform. And now according to this xn, what is xn? According to the inverse discrete Fourier transform, we can write this portion. So xn can be written as this. Okay, so now you can find that there is a relation between x omega and xk. This is the relation between x omega and xk. Now by putting the value, okay, so you can extend the mathematical term and you will find that, okay, this is the final equation where we have x omega. For different value of omega, you can find the value of omega. So this is a function of omega. Now by knowing the value of xk and putting different value of omega, you can find what is the value of x omega. So you can higher resolution of that. Of course, if the gradient of xk is higher, it will give more specific value of x omega. That's for sure. Okay, so probably you need this formula again. So this is from the Euler's the series calculation. Okay, and this is the final calculation. Okay, put the value of xk omega for different value of omega from 0 to pi. You can find the value of x omega. The question is, how can we make the dense representation of xk even though we have a very small number of n? So as we have already mentioned that previously, it was given like this. We have half and half, 0 and 1. So that was your xn. In this case, the value of n is 0 and only 1. So how we can make dense value of xk? We have already mentioned that we can pad with 0 in the time domain to convert the n to m. So that means it is basically capital N was like 0 and 1. Now we can improve it with the value of m, where it might be is equals to 20, it can be equals to 30, whatever you need. So padding 0 is the solution, how to make it dense xk value. Okay. Now we can move to the properties of the DFT. Please go through the book for the detailing of this property. I have shown it in a very concise way, and focus, I have given the focus on the circular shifting or circular convolution mostly. So whatever properties we have found in case of Fourier transform, we have found the same properties here for the discrete Fourier transform. So the linearity must be here. I do not need to, it's not necessary to discuss it here. The shifting property, in case of Fourier transform, definitely Fourier transform, we have shifting. However, in case of discrete Fourier transform, this is known as circular shifting. So I'll discuss this circular shifting more in detail with the diagram. In case of Fourier transform, we have the shifting. This is the time domain shifting. So we are shifting the signals. So if we have two samples here, 0 and 1, if we want to shift it one sample to the right, what will happen? It will shift like this, 1 and 2 and this. So this is xn and this is xn minus 1. So that is the shifting. However, in case of this is for the Fourier transform. Whenever we are doing Fourier transform, this kind of shifting we are doing. But in case of discrete Fourier transform, we are doing the circular shifting. Why that is so? Because as you know that the range of view is from 0 to n minus 1. If I have some sample here, let's say I have the sample here, I have the sample here, maybe at there and there. Okay. If I want to shift it in case of linear shifting, in the linear shifting, so it will go out of the range. That means maybe after the shifting, we got this. This is 0. That is my, I'm just shifting all the signals. Maybe the signals are shifted like this. So as you can find that it is out of the range. So it is not permittable. So in that case, what can be done and what actually been done here? So this sample is taken to the input and the initial stage. So that means this sample is shifted to the first sample. So that means it looks like this. So the output looks like this for the circular shifting, this, then 0, then higher value, and then more higher value. So then it will be restricted from 0 to n minus 1. And this is the concept of the circular shifting. If you want to shift more, so previously that was xn, and now this is xn minus 1. If you want to do xn minus 2, what will be done? This will be shift again to the first. This will be shift to the right, and this will be shift to the right. And this is known as the circular shifting. Okay, I'll give you more example. So that's why, since our range of view is this, we can't go out of that. So that's why the circular shifting is the solution, how to make all those samples inside. Okay. Okay, the example can be shown at like this. Okay, for understanding, this is a linear. Actually, the samples are looks like this. It can be also shown in a circular way. So this is our x0, x1, x2, and x3. This is exactly our xn. This is the mother signal. Now, if we want to shift one sample like xn minus 1, what will happen? Of course, this sample will shift right, and this will shift to the first sample. And that actually been happen. You can find that this will be there, this will be there, this will be there, and this will be shifted to the first sample. And from the circular point of view, you can also find that this x0 is shifting there, x1 shifting there, x2 is shifting, and x3 is shifting to the first location. So this is our xn minus 1. Now we can show it. Similarly, this is xn minus 2. This is xn minus 2. That means now this is shifting again, shifting and shifting, and this will come to the first point. Okay, so the thing is very, very simple. Okay, now one thing, how to mention it mathematically. So as we can understand, in case of linear shifting, if this is your xn, we have mentioned it as xn minus 1. This is for the linear shifting, but for the circular shifting, we should mention how many samples are there, and that's why we need to put a 4. Okay, and how they actually works, try to understand that. For n is equals to 0, it will be x 0 minus 1. What is that? X minus 1 for n is equals to 0. So that means we are targeting this point for n equals to 0 of the new signal. What is the new signal? New signal is n minus 1, 4. For the new signal, for n is equals to 0, where is the mother signal? The mother signal is xn. So this is your mother signal. So x 0 minus 1, it gives x minus 1. Do you have any x minus 1? No. In the mother signal, you do not have any x minus 1 because that is out of range. Then how we can represent that? Try to keep your eye on this equation. It can be also written as x n plus 3. They are equivalent when this minus term comes here. So whenever the output gives that x minus 1, for this one, this part is not valid. In that case, you need to put this n over there. So put n equals to 0, then it gives n3. Where is n3? So this is the n3. Let's say this is your n3, and that should come to your first position, and this is your x3 will be there. So I should write in this way. This is n minus 1. Okay, fine. If you put n is equals to, for any value of n, if you found something like minus 1, then you should go for another equation, which is n plus 3 for this case. For n is equals to where capital N is equals to 4. So you need another formula for that one. So I have shown it here as well. So for this one, this is the general equation. For all other samples, definitely it works fine. In my opinion, what I am doing, you can also follow this process, that x n minus 1, 4, for n is equals to 0, what we can do, x minus 1. What I have done, this is equals to x 4 minus 1, that is x3. Whenever you have minus something, put the value of n before that, 4 minus 1, it will give x3. So then you can find that, okay, the x3 should come to the value of, for n is equals to 0 location. For n equals to 0 location, it will come there. Okay. Okay. For the second example, okay, arbitrarily we can find this is x n minus 2. What is the equivalent equation? The equivalent equation should be x n plus 2 into 4. If I only consider this, how we can find that? Let's, for n is equals to 0, it will have n 0 minus 2. According to my perception, I am putting like this, x 4, since this is a minus, 4 minus 2, which is give x2. So x2 will come. So what is your x2? X2 from the mother signal, definitely x2 is this, and it actually comes to the 0th sample. Similarly, for n is equals to 1, you will find that x1 minus 2, which is give x minus 1. Whenever you have x minus 1, it can be replaced as 4 minus 1, that is x3. And you can find that, yes, x3 actually come to this point. Okay, so it's very simple. You can just follow this process, but physically what happens you need to understand. So you have the original signal. Whenever you are shifting right, shifting right, shifting right, but this one is shifting. It looks like you have a paper, circular one, you are putting some marble here, there, and when this is rotating, it will rotate like this, and rotate like this. Okay, so that is the circular shifting. Another question is, this is the concept. First of all, this is the concept. Now the question is, why the circular shifting actually give us the proper result or actual result? What is the logic behind that? The question might be asked in that way. If I have a signal like this, if I shift right, then what happens? Then 0. If you are shifting right, your signal in the time domain, definitely you have the impact in the frequency domain. So you have xn minus 1. You also have the shifting in the frequency domain. You are getting the same frequency, but the phase will be changes, minus j omega. So some omega part will be changes. I'm just giving some example here. You got my point. So in the time domain, when this is our original signal and this is the shifted signal, of course that makes some sense in the frequency domain. But now we need to understand how this circular shifting also make logical changes in the frequency domain. How that is logical, this circular shifting, how this circular shifting is logical. Okay. Okay, so I believe that we can discuss this in the next class, and we can probably end this discrete Fourier transform in the next class, inshallah. Okay, so if you have any question, do you have any question at this moment? Any question or any comments? Okay, it looks like you don't have any question or comments. Then thank you for your participation. Thank you.